Euler's method is a way to approximate a point of a function when one is only given its differential equation and an initial condition. Obviously, this process is only useful when the given differential equation cannot be integrated. First example, I'll use a differential equation that we can integrate. Our differential equation is dy dx equals y. Our initial condition is the point 0, 1. And this is an integrable differential equation, and this is the actual solution curve. The first step in the process of Euler's method is to draw the first tangent line at the initial point. And so in this problem, that's at 0, 1. Alright, and now we need to decide on a step size. The step size essentially determines how often we reevaluate the slope of the tangent line approximation. For this example, let's use a step size of 1. So our step size is 1, so we'll mark the point on our initial tangent line at x equals 1. Alright, and then we're going to reevaluate the slope after that point, so I'm going to go ahead and erase the rest of that tangent line. We don't need it. Alright, so then we reevaluate the slope from that point. Something like that. Alright, and then we'll reevaluate the slope again. And then the last one from 3 to 4. And this last point is our approximation for y of 4. It's not too far off, but you can see that with each new iteration, it's getting farther away from the actual curve. The smaller the step size you use, the more accurate your approximation will be. Updating the slope more frequently will keep the approximation lines closer to the actual function. So this is a graphic representation of Euler's method, but it's far more useful to have a concrete formula, and so that's what we'll develop right now. To develop the formula, we just need to manipulate the equation of a tangent line. So our equation for a tangent line, y minus y sub 0 equals m times x minus x sub 0. We know that h is the step size, so it's also the difference in x between each iteration. So we can replace this x minus x sub 0 with h. Okay. Alright, and we know each iteration will be looking for the next new y value, and so we should try to isolate that. So y equals y sub 0 plus mh. M is the slope of the tangent line, and the slope of the tangent line will be the same as the differential equation with those x and y values corresponding to the point. So y equals y sub 0 plus f x sub 0 y sub 0 times h. So to generalize it for multiple steps, we can write it like this: y sub n plus 1 equals y sub n plus f of x sub n y sub n times h. So what this tells us is that the next y value is going to equal the former y value plus the step size times the differential equation at that point, or the slope of the tangent line, whichever way you prefer to think of it. So now we'll do an example with that formula we just got. Using Euler's method with a step size of 0.5, approximate the solution to the following differential equation at x equals 3. dy dx equals sine of x to the 4th with the initial condition of 0, 3. Okay, so now let's just do out the whole first iteration. So these are the values of our initial condition. Our initial y value is 3, our initial x value is 0. And so what we want to do is find y sub 1. So using this equation, we know y sub 1 equals y sub 0, which is 3, plus the step size, which was given to us in the problem, so 0.5 times the differential equation with x sub n and y sub n plugged in there. So in this case, there's no y sub n in the differential equation, so we just plug in x sub n, or x sub 0 in this iteration. So sine of x to the n, sine of 0 to the n, 1 equals 3 plus 0.5 times sine of 0 is 0, so 0. So y of 1 equals 3. You should start to make a table so we can keep track of all of these iterations. Every iteration, but it just goes the same way as the first time. Y of n plus 1 equals y of n plus h times the differential equation at x sub n, y sub n. So our last iteration yielded 3.32763 approximately, and that is our approximation.